Problem is, again, that's not our world. That bears very little resemblance to the Big Bang and so forth. Now, to their credit, Brian Greene and some of his collaborators tried to make something like this that is more like the real world. So this is an action for a field theory. You don't need to worry about the details. The point is, they say, what if in the real world, the world that has the Big Bang and general relativity and so forth, what if the strength of gravity, the strength of Newton's constant of gravity, is not a constant, but what if it varies? And this is a very old idea, going back to Dickey and Dirac for that matter. They say, what if it varies in such a way that in the very, very early universe, gravity was turned off? So remember, it was the smoothness of the configuration of the early universe that gave it a low entropy, because when gravity is important and the density is high, things want to form black holes. The fact that the early universe was smoothly distributed was a surprise. That's a low entropy state. But they say if there's no gravity in the early universe, then it's not a surprise. If there's no gravity, then a thermal distribution is a high entropy state. So they have a field that controls the strength of gravity, and it evolves from being a very tiny number, effective value of Newton's constant at early times, to a larger number today, which asymptotes to some constant value. So they say maybe that can explain why the early universe was so smooth, because gravity was turned off. I think this is sort of, again, admirable. I think it's a step in an interesting direction. I don't think it's the right theory of the real world. It's compatible with the fact that the early universe is smooth, but it doesn't really explain the actual configuration of the universe we see. The actual early universe is not only smooth, it's incredibly dense, which is not explained by this, and the specific features of the early universe don't seem robust under this scenario. It does not seem to be the case that no matter what conditions I gave you initially, you would evolve into what we see as the early universe. I think that's a stronger requirement, and this doesn't quite live up to it. Said yet another way, I said that the high entropy state in theory that we understand is empty space, de Sitter space with nothing in it, at a low value of the energy density, and we should be Boltzmann brains in that background. I don't see why in this scenario that's not true. I don't see why we don't live in empty space. So the final scenario I want to float by you is still my favorite, even though I'm not at all attached to it too strongly. But it's a top-down approach. So rather than saying, here's the universe that we see, starting from the Big Bang, etc., how can we explain that? This scenario says, if all the reasoning I gave you is right, the conclusion should be that we are Boltzmann brains in empty space. Most observers should find themselves fluctuating out of thermal equilibrium in an empty universe. So why aren't we then? Let's start there. Let's start in this robust, nominally high entropy configuration, which is just empty space, and say, how can we escape? Can there be some dynamics that start with something that looks like high entropy and nevertheless creates our universe? And as far as I can tell, the only answer that is on the table within the theories that we think about these days are transitions between different vacuum states. So the point here is that in some field theory or some string theory or some ultimate theory of everything, there'll be all sorts of different fields. And it's kind of like ice, water vapor. Depending on the local conditions, there are different states, different phases that the theory can find itself in. So our theory of the universe right now, with a small cosmological constant, with electrons and protons and so forth, is one phase that the universe can find itself in, but maybe there are many different phases. And these different phases will have different values of the vacuum energy. And that different value of the vacuum energy will affect the expansion of space-time in a dramatic way. So in other words, we live here. Maybe the escape from being cold and empty in de Sitter space is that we can bounce around between these different vacua and they all look different to us. So what I mean by that is, let's take a toy model of this where there's only two vacuum states. And this is a theory that is studied to death by cosmologists, but they always start here and they study transitions going downwards. So they start with a high value of the energy density in empty space, and they show how it can decay to a lower value. That's the easy part because the entropy increases when you do that. That's the natural thing to happen. But if you wait forever, it's possible that there are fluctuations upward in energy density. So it's possible, and now we're just guessing. A lot of long papers with equations have been written about this, but it's not on firm ground. It's possible there are fluctuations where both the energy density of empty space changes and space itself bends, so there's a little bulb that is a baby universe that can pinch off and grow by itself. So what we're imagining is here is a fluctuation of space and simultaneously a fluctuation in some fields, which means that this little ball of universe has a much higher effective vacuum energy than the background from which it came. And this should happen just through thermal fluctuations. And plausibly, this little piece of space expands at a tremendous rate, because now it has a tremendous vacuum energy. Right? Vacuum energy causes space to expand. So this is inflation. This is a theory that is known to be considered taken very seriously applied to our early universe. What would happen is, starting from this little tiny ball, the universe would expand under the influence of this vacuum energy by a tremendous amount, and that vacuum energy would decay back to where it started, and all its energy would go into reheating the universe into matter and radiation, and it would all be in a very smooth, rapidly expanding configuration, just like the Big Bang we actually see. So the idea here is that the difference between this scenario and Boltzmann scenario is that the entropy is not maximum when you're in this background. You can increase the entropy by making new universes. So the space-time picture of something like this is that you start, now I'm running time left to right to make it look less prejudicial about up and down. You start in what you thought was a high entropy state, empty space. Nothing happening, cold, emptiness, except for some thermal fluctuations. But you make a little bubble that expands and creates a universe. Now that's something that could happen. You could also make a little brain. Okay? And so there's some counting problem that needs to be solved in a theory like this, where when you should be able to compare the number of brains to the number of observers that arise in these universes that pinch off. Nobody knows how to do that. But the hope is that because the bubbles of baby universes are smaller, they're easier to make than brains. I don't know how to quantify the amount of hope that goes into that hope, but you know, it's the Obama administration, we can be hopeful, right? We can hope. The best thing about this is you can tell the story both directions in time. So you start, remember, I'm working in theories that have no starting point for time, so I should have a boundary condition for the universe, and I evolve it in both directions. So my boundary condition is I try to make it as high entropy as I can, which means empty space. I evolve it forward, I make all sorts of baby universes, and they have their arrows of time for a while before they empty out to just become de Sitter space themselves. But I also evolve it backward in time, and the same thing happens. I make baby universes that increase in entropy that way. So just like the ball of gas in an otherwise empty universe, the entropy can increase forever in this model, and does increase both to the far future and to the far past. And just like Boltzmann, I say that if you live in one of these universes, you define the past as your local direction of lower entropy. So to us, here, these guys are in the past and have a backwards going arrow of time. But these guys don't see omelets turning into eggs. They just say that this direction is the future and we are in their past. And the whole multiverse is completely symmetric in this scenario. So at least I'm not cheating by putting the arrow of time in by hand. It comes out dynamically in both directions. So this is the conclusion slide. Remember where we are going here and where we are. I just want to bring up as possibilities the idea that the Big Bang is not necessarily the beginning of the universe. We still are allowed to consider theories where time lasts forever and everything evolves unitarily in a reversible fashion. In fact, I think that's the most likely, most conservative possibility. What we need to explain is not only the existence of entropy gradients, because that's easy to explain. We need to explain why, if there's an entropy gradient, it's probably part of a large entropy gradient to avoid the Boltzmann brains. If you want to try to do this in the context of reversible unitary laws, I think that the implication is that you should have arrows of time both towards the past and towards the future. You need an unbounded entropy in your system. Otherwise, if the entropy is bounded, you will get there and you'll stay there forever. The problem, this is easy to solve all these problems. The problem is making a scenario that also matches the real world, explains our actual early universe with the Big Bang and so forth. Why is it like that? Maybe it's because of baby universes. Maybe it's some other trick of de Sitter space and multiple vacua and things about quantum gravity we don't yet understand. But it's not completely impossible to imagine a future in which we do understand these things. It's possible to imagine a future where the theory of everything says, no matter what state you put me in, I will evolve to make universes like the universe that we live in that have a local arrow of time. That's why we see it